November 24, 1944. Northfield, Tinian, and Elliefield, Saipan. The 21st Bomber Command launches 111 Boeing B-29 Superfortresses toward the Japanese mainland. Brigadier General H. Wood Hansel commands the American Strategic Bombing Force from his headquarters on Guam. Silver bombers, carrying 277 tons of bombs, against the Nakajima Aircraft Company's Musashino engine plant on Tokyo's outskirts. What Japanese fighter pilots discover this morning will shatter their understanding of aerial warfare and reveal a technological gap that no amount of courage or determination can overcome. Captain Tatsuo Yamada adjusts his oxygen mask in the cockpit of his Kawasaki K-61 Heian at Chofu Airfield outside Tokyo. The morning briefing emphasized intercepting enemy bombers with maximum altitude advantage. Intelligence reports indicate large four-engine bombers operating from newly captured Mariana Islands bases, flying at unprecedented heights. Yamada volunteers for the high-altitude interception mission that promises difficult combat against an enemy whose capabilities remain largely unknown. His aircraft carries four 12.7mm machine guns and two 20mm cannons, weapons designed for combat at conventional altitudes where Japanese fighters excelled. The altitude challenge emerged from Japan's limited experience against American heavy bombers in China during early 1944. Those B-24 Liberators and older B-7 Flying Fortresses operated at altitudes Japanese fighters could reach, typically between 20,000 and 25,000 feet. Major Tishi Meda had developed specialized climbing tactics based on those encounters, emphasizing gaining altitude before engagement rather than climbing during combat. A pilot already at altitude possessed energy advantages that could overcome defensive armament, but the morning's intelligence reports suggested these new bombers operated far higher than anything previously encountered. The 21st Bomber Command represents America's most powerful Pacific strategic deployment since the Dittle Raid of 1942. The command would eventually total over 1,000 aircraft operating from 5 major airfields across Saipan, Tinian, and Guam, with pressurized cabins designed specifically for extreme high-altitude operations over vast Pacific distances. This construction philosophy differed fundamentally from previous American bombers. The B-17 Flying Fortress and B-24 Liberator used unpressurized crew compartments that required heavy flight suits and oxygen masks, limiting their effective operational ceiling to around 25,000 feet. American designers prioritized altitude capability in the B-29, accepting complexity in exchange for operational sanctuary above enemy interceptor range. The pressurization system allowed crews to work in shirt sleeves at altitudes where unpressurized aircraft crews would struggle with cold and hypoxia. Yamada's formation includes K-61 High-End from the 244th Century and Nakajima K-44 Shoki interceptors from the 47th Centi, climbing desperately from multiple airfields around Tokyo at maximum sustainable rate. The Japanese pilots observe contrails forming at extreme altitude, where American formations approach from the southeast. Radar operators at the Chiba Detection Station identify the incoming formation at 27,000 to 31,000 feet, varying their altitude as they navigate weather conditions. Ground controllers vector defending fighters toward the threat axis, but the climbing interceptors struggle to reach even 25,000 feet before the bombers arrive over target. The technological disparity becomes immediately apparent as opposing forces attempt engagement for the first time. Yamada flies an aircraft designed in 1941 for medium-altitude combat against Chinese and early Pacific War opposition. His Kai-61 weighs 7,650 pounds, lb with a 1,175 horsepower. Kawasaki HR-40 liquid-cooled engine providing 368 miles per hour, maximum speed at 16,400 feet. While specifications claim a service ceiling of 36,000 feet, actual combat performance degrades severely above 28,000 feet. The engine loses power dramatically in thin atmosphere, while control surfaces become increasingly sluggish. Self-sealing fuel tanks and pilot armor had been incorporated following combat experience, adding weight that further reduced altitude performance. The Kai-44 interceptors from the 47th Centi attempt reaching the bomber formation, which varies between 27,000 and 30,000 feet altitude, depending on weather conditions. These fighters, specifically designed for high-altitude interception with superior climb rates, struggle desperately in the thin atmosphere. Engines overheat while producing a fraction of their sea-level power, and pilots gasp through inadequate oxygen systems that were designed for shorter engagements at lower altitudes. The interceptors manage to reach 28,000 feet before most begin stalling, still thousands of feet below many of the bombers. Those few fighters that achieve sufficient altitude lack the energy for sustained engagement. Control surfaces barely respond in rarefied air, while engines strain beyond design limits. The B-29 seconds maintain formation integrity at their operational altitude. Crews working comfortably in pressurized compartments without the heavy flight suits or cumbersome oxygen masks that handicapped previous bomber operations. Captain Robert Morgan commands the lead Superfortress Dauntless Doy as navigator. Captain Theodore Vanserk identifies the primary target through the Norden bombsight. The bomber's 4 Wright 350 engines generate 2,200 horsepower each, maintaining over 300 miles per hour's true airspeed at operational altitude despite the thin air. Turbo-superchargers compress the thin atmosphere, maintaining engine power where naturally aspirated engines fail. The pressurized compartments connect through a tunnel over the bomb bays, allowing crew movement without altitude suits. This design enables sustained operations at altitudes previously impossible for combat aircraft. The central fire control system coordinates defensive armament through analog computers, tracking multiple targets simultaneously, while gunners operate from comfortable positions. Yamada pushes his K-61 to absolute ceiling, the airspeed indicator showing barely 180 miles per hour as the fighter wallows in thin atmosphere approaching 30,000 feet. His pre-war training never anticipated combat at such altitudes. The mission briefing emphasized attacking from above using diving passes to maintain energy, but reaching position above the bombers proves impossible. Japanese doctrine developed against unescorted B-17S and B-24 seconds operating at moderate altitudes proves completely inadequate. The high-end sustains 30,000 feet for mere seconds before stalling, forcing recovery that costs 3,000 feet of altitude. Multiple attempts achieve similar results as engine temperature gauges exceed redline limits and oil pressure fluctuates dangerously. Yamada observes bomber contrails passing overhead, their defensive guns tracking his fighter but not firing due to extreme range. The altitude gulf prevents any meaningful engagement, despite desperate Japanese efforts and early warning of the raid. That morning, only 40 Japanese fighters managed to make any attacks on the bomber formation, most achieving just single firing passes before losing energy. Machine gun rounds fired in climbing attacks lose velocity rapidly in thin air, many falling short of targets. The few fighters reaching effective firing position possess insufficient energy for sustained engagement, managing only brief bursts before stalling away. Anti-aircraft shells explode thousands of feet below the bombers, despite maximum elevation settings on the guns. The largest Japanese anti-aircraft weapons can theoretically reach 30,000 feet. But accuracy at such altitudes proves virtually impossible. The November 24th raid marks the first mass B-29 attack on Tokyo since the symbolic Dittle raid 31 months earlier. The formation maintains course toward the Nakajima Aircraft Company's Musashino engine plant, Japan's most important aircraft engine manufacturing facility. Chief Bombardier Lieutenant Coleman releases his bombs on signal, followed by other aircraft dropping in sequence from their varying altitudes. Due to powerful G-stream winds discovered at altitude reaching over 200 miles per hour, only 24 aircraft hit the primary target, with others bombing secondary targets or missing entirely. Yet the psychological impact proves profound. The bombs fall from unprecedented altitude, while Japanese fighters circle helplessly below, unable to reach the attackers. Ground observers watch vapor trails crossing Tokyo's sky at previously unimaginable altitude beyond reach of defending fighters. Lieutenant Kenji Tanaka coordinates fighter operations from sector control, receiving frustrated reports from interceptor squadrons. Pilots report engines failing, controls becoming ineffective, and inability to sustain altitude necessary for interception. The bombers proceed through Japanese airspace, suffering only one loss to a ramming attack by a damaged fighter in a suicidal gesture of desperation. Defending pilots expend fuel in futile climb attempts, most returning to base without ever reaching firing range. The technological superiority displayed shocks Japanese military leadership and pilots alike. The 21st Bomber Command concludes its first Tokyo mission with minimal damage from defenses, though mechanical issues force several B-29 seconds to divert or ditch in the Pacific. Japanese fighters claim only one confirmed victory through ramming, while bomber gunners claim 5 Japanese fighters destroyed. The altitude sanctuary contradicts every Japanese expectation based on intercepting lower-flying bombers from China bases. This operational failure stems from fundamental misunderstanding of American bomber capabilities and the revolutionary nature of the B-29's design. Lieutenant Commander Minoru Genda observes B-29 operations from Naval Headquarters, analyzing Army fighter failures with growing concern. His intelligence reports emphasize the unprecedented bomber altitude that exceeds Japanese interceptor capabilities by significant margins. Even the Navy's latest fighters cannot effectively engage at such heights. The strategic implications suggest requirements for completely new aircraft designs or alternative defensive methods, but Japan lacks time and resources for such development. The intelligence failure reflects limited technical information about American pressurization technology and turbo-supercharged engines, innovations that transformed high-altitude operations. Japanese planning had assumed enemy bombers would operate at conventional altitudes below 25,000 feet. Based on all previous experience, the B-29's pressurized cabin concept remained poorly understood by imperial military analysts, who failed to grasp its implications for combat operations. Previous American bombers operating from China bases flew at altitudes Japanese fighters could reach, reinforcing these assumptions. December 3, 1944, brings another concentrated B-29 attack against Tokyo, with 86 aircraft targeting the same Musashino plant. The Japanese response evolves based on the November experience. Captain Teruhiko Kobayashi of the elite 244th Senti implements new tactics, positioning his fighters at maximum altitude before the bombers arrive, hoping to dive on them with energy advantage. But, even starting from optimal position, the K-61S cannot reach bomber altitude. The formation includes specially modified interceptors with reduced armor, removed radios, and minimal ammunition to save weight. These stripped fighters achieve marginally better altitude, but still fall short of effective engagement height. Lieutenant Saburo Hayashi leads a specialized ramming unit called Hagakur Tai, formed from volunteer pilots willing to sacrifice themselves. The unit's aircraft strip all unnecessary weight, including most armament and armor protection, carrying only enough fuel for one-way missions to achieve maximum altitude. The modified K-61 fighters climb toward the approaching formation with emergency boost engaged, accepting certain engine damage. Manifold pressure exceeds manufacturer limits, while cylinder head temperatures approach failure point. Pilots pre-B breathe pure oxygen for 30 minutes before takeoff, but the inadequate oxygen systems still cause hypoxia symptoms during extreme altitude attempts. Most fighters stall around 30,000 feet, still below effective engagement altitude. Sergeant Masawaki achieves 31,500 feet in his lightened K-61 before attempting a ramming attack against a straggling B-29. The bomber's defensive guns fire continuously as the fighter approaches from below in a zoom climb. Multiple 50-caliber rounds strike the Ki-61, but Itaki maintains his collision course. At the last moment, his fighter loses energy, stalling 500 feet below target, before entering an uncontrollable spin. The pilot recovers at 20,000 feet. His aircraft, too, damaged and lacking fuel to attempt another climb. The ramming attacks achieve occasional successes when bombers descend due to mechanical problems, but cannot systematically counter the high-altitude threat. Through December 1944, B-29 losses remain minimal, while Japanese cities begin suffering strategic damage. The defending pilots experience profound frustration, watching their homeland attacked while remaining powerless to intervene effectively. Traditional samurai warrior spirit proves meaningless against technological barriers, preventing combat engagement. Pilots report feelings of helplessness and shame at their inability to protect Japan, despite willingness to sacrifice their lives. Major General Curtis Lame assumes command of the 21st Bomber Command in January 1945, analyzing high-altitude daylight raid effectiveness with his characteristic intensity. Initial missions achieve poor accuracy due to the jet stream winds discovered at bombing altitude, sometimes exceeding 250 miles per hour. Powerful high-altitude winds, later known as the jet stream, create unexpected challenges for B-29 operations over the Pacific. These winds push bombers rapidly across their targets, making precise bombing nearly impossible. Navigation becomes increasingly difficult. Even the most skilled bombardiers see their bombs drift miles off course, while thick winter cloud cover often forces radar-guided attacks with limited accuracy. As a result, less than 10% of bombs reach their intended targets. General Curtis LeMay faces growing pressure from Washington to improve results. After analyzing the situation, he orders a major tactical shift in March 1945, switching to low-altitude night operations using incendiary weapons. This decision fundamentally transforms the air campaign over Japan. B-29 seconds are stripped of most defensive guns except for the tail turret, allowing them to carry maximum bomb loads. Flying at altitudes between 5,000 and 9,000 feet eliminates the jet stream problem, but also brings the bombers within range of defending interceptors and anti-aircraft fire. On the night of March 9th, 1945, Operation Meeting House begins a massive low-level raid over Tokyo that reshapes aerial warfare. A total of 334 B-29 seconds approach the target area under cover of darkness. The sudden change in altitude and timing catches defenders by surprise. Lieutenant Yoshio Mitsuyoshi takes off from Matsudo Airfield in his Nakajima Ki-44, now able to intercept at the same altitude as the bombers. Night combat, however, proves chaotic. Without onboard radar or effective ground direction, defending pilots struggle to locate their targets. Searchlights sweep the skies, briefly illuminating isolated bombers as anti-aircraft guns open fire at close range. Individual interceptors conduct uncoordinated attacks without radio communication or formation tactics. Mitsuyoshi manages several firing passes, hitting multiple engines and fuselages, but most bombers continue on course despite visible damage. The B-29's rugged design allows many to survive hits that would have downed smaller aircraft. Its remote-controlled turrets, directed by onboard radar, prove unexpectedly effective in the dark, forcing interceptors to disengage after short exchanges. The incendiary attack ignites a massive firestorm that engulfs much of Tokyo, destroying roughly 16 square miles of the city. Defending aircraft claim 14 B-29 seconds destroyed the highest number in a single operation, but the scale of the attack overwhelms available defenses. The effectiveness of the new tactics validates LeMay's decision and sets the model for subsequent operations. This tactical evolution also renders many high-altitude interceptor programs obsolete. Aircraft and engine projects designed to reach 30,000 feet or higher lose relevance as the bombing campaign shifts to lower levels. In early 1945, Navy Lieutenant Sadamu Kumachi flies the new Mitsubishi J-2M Raiden interceptor during air defense operations over Nagoya. The aircraft's supercharged engine provides an impressive service ceiling of 36,000 feet, theoretically capable of reaching B-29 formations. In practice, however, extreme altitude combat proves difficult. Control surfaces respond sluggishly, engines produce minimal power, and pilots often report oxygen system issues causing fatigue or disorientation. Even when interceptors reach bomber altitude, maintaining stable pursuit or effective firing solutions becomes nearly impossible. Most successful engagements occur against damaged or isolated bombers descending from formation rather than intact aircraft at cruising altitude. The shift to low-altitude raids further reduces opportunities for high-altitude fighters to engage effectively. By April 1945, defensive forces begin employing new, last-resort tactics. Special attack units are organized to directly target B-29 seconds when conventional interception fails to achieve sufficient results. On April 12th, Corporal Koshio Gawa destroys a B-29 over Kawasaki in a collision that costs both aircraft. That same day, another dramatic event unfolds aboard a B-29 when Staff Sergeant Henry Irwin earns the Medal of Honor after a phosphorus flare accidentally ignites inside his aircraft. Severely burned and temporarily blinded, Irwin manages to carry the burning flare to an open window and throw it clear, saving his crew and aircraft. The device burns through Irwin's face and body, destroying his nose and blinding him. Despite horrific injuries, Irwin carries the flaming device through the bomber to the cockpit window, saving 11 crew members. His sacrifice exemplifies the courage shown by both sides despite the technological mismatch. Special attack units form at multiple bases, with pilots volunteering for certain death missions against the Silver bombers. These ramming attacks achieve limited success, destroying perhaps 10 B-29s throughout the war, a tiny percentage of the bomber force. The psychological strain on American bomber crews intensifies as they face opponents willing to sacrifice themselves in mid-air collisions. Although these extreme tactics cause anxiety among airmen, they do not significantly alter the overall effectiveness of the bombing campaign. The B-29's centralized fire control system proves highly efficient against intercepting aircraft, despite having fewer gun positions than earlier bombers like the B-17. Its computer-assisted turrets can track multiple targets at once, with gunners operating from pressurized compartments inside the fuselage rather than exposed positions. Defending pilots report unusually precise defensive fire, as the automated tracking system maintains accuracy even during evasive maneuvers. Because the system allows continued operation even when individual turrets are damaged, the bombers remain protected throughout their missions. This technical advantage, combined with the aircraft's high operational ceiling, reinforces the sense of safety for American crews during high-altitude missions. The arrival of long-range P-51 Mustang escorts from Iwo Jima in April 1945 further transforms the air war over Japan. These fighters establish near-total air superiority, making daylight B-29 operations significantly safer. Japanese interceptors now face the added challenge of contending with aggressive escort fighters before they can reach the bombers. Those that break through the escort screen often find themselves pursued before achieving effective firing positions. Captain Yasuhiko Kuro, commanding the 64th Sentai, equipped with Nakajima Ki-84 Hayate fighters, Japan's most advanced operational aircraft, reports improved performance at medium altitudes. Under ideal conditions, the Ki-84 can reach about 34,000 feet, but practical ceiling performance typically peaks near 28,000 feet due to engine power limitations at high altitude. The Ha-45 engine provides excellent medium-altitude power, but lacks effective supercharging for extreme heights. Ki-84 seconds achieve limited success, intercepting B-29 seconds during lower-altitude mine-laying missions, scoring several victories when altitude differences are reduced. These engagements highlight the aircraft's capability when conditions allow, but high-altitude daylight raids remain largely unopposed. In June 1945, the Kawasaki Ki-100 enters service, a modified version of the earlier Ki-61, fitted with a more reliable radial engine. While this change greatly improves reliability and ease of maintenance, it also reduces high-altitude performance. Pilots praise its handling and maneuverability at medium altitudes, but its service ceiling of around 32,000 feet remains insufficient to engage B-29 seconds operating at their maximum height. Japan's aviation industry continues developing several specialized high-altitude interceptor prototypes throughout 1945. The Mitsubishi Ki-83 twin-engine fighter shows exceptional potential with turbo-supercharged engines, while the Kawasaki Ki-102 heavy fighter carries heavy armament designed for bomber interception. However, material shortages, especially high-grade aluminium and heat-resistant alloys for superchargers, cripple production efforts. Repeated bombing raids further disrupt manufacturing, destroying factories and engine plants before these advanced aircraft can be deployed operationally. By early 1945, the destruction of major facilities, such as the Akashi Engine Works, responsible for producing Ha-40 engines, effectively ends large-scale fighter production. The technological gap between Japan's aircraft and America's B-29 seconds continues to widen, with the US introducing improved models and tactics every month, while Japan's industrial capacity declines. During this period, Lieutenant Colonel Paul Tibbets oversees specialized training for atomic bomb delivery operations, utilizing modified silverplate B-29 seconds. These aircraft are stripped of nearly all defensive weapons except the tailgun, allowing higher operational ceilings and extended range. Their increased altitude and reduced weight make them nearly unreachable by interceptors. On August 6, 1945, this advantage is demonstrated during the mission over Hiroshima. The B-29 Enola Gay approaches its target at an altitude of 31,600 feet. Interceptors scramble from nearby bases, but none can reach the bomber's height. Lieutenant Matsuo Yasui, flying a Ki-61, climbs to 29,000 feet before his aircraft stalls still below the bomber's flight level. Other pilots face similar limitations, unable to close the distance despite ideal weather and full engine power. During the final phase of the campaign, long-range aircraft demonstrated the importance of advanced engineering in high-altitude operations. Their ability to operate far above conventional interception range showcased the impact of technological progress on strategic aviation. Post-operation studies revealed significant differences in pressurization, engine design, and material science between opposing air forces. The introduction of reliable pressurized cabins allowed crews to perform effectively in extreme altitudes, where earlier aircraft could not function efficiently. Turbo-supercharged engines maintained stable power output in thin air, marking a turning point in aerial propulsion technology. These innovations, combined with improved flight control and remote weapon systems, fundamentally changed how long-range missions were executed. Engineers and pilots on both sides displayed exceptional skill and determination in adapting to rapid technological changes. However, limitations in manufacturing capacity and material supply during wartime conditions prevented some nations from matching the pace of development. The campaign demonstrated that technological readiness, more than numerical strength or tactical creativity, often determines the outcome of large-scale operations. The experience underscored the necessity of sustained research, industrial capacity, and engineering collaboration. In the years following the war, global aviation industries analyzed these lessons extensively. Many adopted design philosophies that emphasized reliability at high altitude, efficient pressurization systems, and advanced engine performance. These insights directly influenced the creation of post-war jet aircraft and the evolution of modern aerospace engineering. Former pilots and engineers later described their experiences as a moment of profound transformation in aviation history. The campaign revealed not only the limits of existing technology, but also the boundless potential of human innovation when science and necessity converge. The operational data gathered during these missions became foundational for future strategic aviation doctrines worldwide. High-altitude capability, automation, and environmental control systems, once revolutionary, became standard expectations in aircraft design. Ultimately, these developments shaped the direction of both military and civilian aerospace technology for decades to come, proving that engineering superiority and adaptability are the defining factors in modern air power. Turbo supercharging represents precision engineering requiring special materials and manufacturing tolerances unavailable in wartime Japan. Remote control defensive systems employ analog computers more advanced than any Japanese military equipment, using vacuum tubes and precision components Japan could not produce. The technological examination provides sobering assessment of industrial development requirements for modern aviation competition. Veteran B-29 pilot Colonel Paul Tibbets reflects on altitude advantage during atomic missions. Flying above enemy fighter capability enabled precise navigation to target without defensive concerns. We knew Japanese fighters couldn't reach us, which allowed complete focus on the mission. The technological sanctuary proved absolute. They could see us, track us on radar, but couldn't touch us. It was like being behind bulletproof glass. Their inability to intercept guaranteed atomic mission success, regardless of early warning or preparation. Ki-84 pilot Captain Iwa Hayashi describes attempting B-29 interception during war's final months. Despite flying Japan's most advanced fighter, reaching bomber altitude remained nearly impossible. The engine would cough and sputter above 30,000 feet, barely producing enough power to maintain flight. Controls became mushy, like flying through molasses. We'd make one pass if lucky, firing a short burst before stalling. Watching them continue unharmed while our cities burned below created a sense of helplessness I'll never forget. Analysis of crashed B-29s reveals sophisticated construction exceeding Japanese manufacturing capabilities entirely. Pressurized compartment design incorporates complex sealing systems using synthetic rubber compounds Japan could not produce. Structural reinforcement for pressurization requires precision welding techniques and quality control beyond Japanese standards. Remote turret control systems employ analog computers using vacuum tube technology more advanced than any Japanese military equipment. The servo mechanisms for gun control demonstrate precision manufacturing unavailable in Japanese industry. Even basic components like electrical wiring use materials and insulation superior to Japanese equivalents. Major Toshio Sakagawa commands the 244th Sentai during B-29 offensive, recording unit combat experiences. My pilots were among Japan's best, with years of combat experience, yet we achieved virtually nothing against B-29s at altitude. Our combat reports consistently describe the same failure, climbing desperately, reaching perhaps 28,000 or 29,000 feet, engines failing, controls becoming ineffective, then watching helplessly as bombers passed overhead. The technological defeat was complete and humiliating. Binkner Bombardier Lieutenant Marcus McDilder observes Japanese fighter attempts during missions over Osaka. The Japanese pilots showed incredible determination. We'd watch them climbing toward us for 15 or 20 minutes, struggling higher and higher. Some would try zoom climbs, trading speed for altitude in desperate attempts to reach us. They'd fire a few rounds, usually falling short, then stall and spin away. Our gunners rarely needed to fire. The altitude was better protection than any armor or weapons. It was a completely one-sided fight, determined by technology, not courage. Japanese military attaché reports from Germany describe Luftwaffe difficulties intercepting high-altitude Allied bombers, providing context for Japan's struggles. Even with superior engines and technology, German fighters faced challenges engaging bombers above 25,000 feet. Mi-262 jet fighters achieve limited success through speed and altitude performance advantages unavailable to Japan. Japanese industry cannot develop equivalent jet technology before war's end. Despite recognizing the requirement, attempts to copy German designs fail due to lack of special materials and manufacturing expertise. The technological gap proves unbridgeable given resource limitations and strategic bombing damage to industry. Colonel John Montgomery leads the 9th Bombardment Group missions from Tinian, observing Japanese defensive evolution. Initially, they tried mass interceptions, sending up everything that could fly. By spring 1945, they'd largely given up on daylight high-altitude interceptions. They concentrated on night raids when we came in low within centuries. Smart adaptation, but too late to matter. The altitude advantage we enjoyed for most of the campaign meant we could destroy their industry almost unopposed. Maintenance officer Captain Hiroshi Fujiwara documents chronic problems with Japanese high-altitude fighter operations in technical reports. Engine failures increased exponentially during maximum altitude attempts. The HAR-40 engine in Kai 61 seconds would overheat within minutes, at full throttle above 25,000 feet. Oil pressure dropped. Coolant boiled despite radiator modifications. Oxygen system malfunctions caused numerous pilot casualties, men passing out at altitude, some never recovering consciousness. Frostbite became common as pilots removed gloves to manipulate controls at extreme altitude. The cumulative mechanical failures made sustained high-altitude operations impossible regardless of pilot determination. B-29 Engineer Staff Sergeant James Pearson monitors pressurization systems during combat missions. The cabin altitude stayed at a comfortable 8,000 feet equivalent, while we cruised above 30,000. We worked in shirt sleeves, moving freely between stations. Meanwhile, Japanese pilots were struggling with frozen controls, inadequate oxygen, and engines that could barely function. The technological mismatch was absolute. It wasn't a fair fight. It was barely a fight at all. Japanese radar operator Corporal Shigo Yamamoto tracks B-29 formations approaching at unprecedented altitude. Our equipment could track them from hundreds of miles away, giving our fighters plenty of warning. But warning meant nothing when our planes couldn't reach bombing altitude. I'd vector fighters toward intercept points, knowing they'd fail. Pilots would report maximum altitude achieved, usually 27,000 or 28,000 feet. Then watch bombers pass overhead at 31,000. The frustration in their voices was heartbreaking. We had the will, but not the means. Final Japanese military assessments acknowledge complete failure defending against B-29 high-altitude operations. Despite geographic advantages, warrior spirit, and early warning capabilities, technological inferiority prevented effective homeland defense. Industrial capacity limitations made matching American bomber technology impossible during wartime. The recognition of technological defeat influenced military support for surrender negotiations, acknowledging that continuing resistance could not prevent Japan's destruction from the air. Lieutenant Kunio Tanaka flies final interception sortie, August 14, 1945, against reconnaissance B-29 conducting damage assessment photography. His Ki-100 fighter achieves 28,000 feet before engine power loss forces descent, typical of hundreds of failed interceptions. The photo reconnaissance aircraft proceeds unmolested at 35,000 feet, documenting atomic bomb damage for American intelligence. The mission symbolizes continuing technological inability to counter American strategic aviation superiority, even in war's final hours. B-29 radio operator Sergeant William Ale monitors Japanese fighter control frequencies during missions, providing insight into enemy frustration. We could hear their ground controllers vectoring fighters toward us, giving altitude and heading information. Then the pilots would report they couldn't climb any higher, engines overheating, losing power. Sometimes you'd hear anger, sometimes resignation. They knew where we were, knew what we were doing, but couldn't stop us. Technology determined everything. The United States Strategic Bombing Survey conducts extensive analysis of Japanese fighter effectiveness against B-29 operations. High-altitude daylight raids suffered minimal losses to fighter interception throughout the campaign. Approximately 50 B-29s lost to fighters from over 30,000 individual sorties, a loss rate of less than 0.2%. Japanese fighters proved effective only when B-29 seconds operated at reduced altitude due to mechanical problems or tactical requirements. The statistics validate altitude sanctuary effectiveness against contemporary interceptor technology. Former Imperial Japanese Navy Commander Masatake Okumiya evaluates strategic bombing defense failures in post-war analysis. The B-29's altitude capability exceeded our intelligence estimates by at least 5,000 feet. We expected maximum operating altitudes around 26,000 feet, based on B-17 and B-24 performance. When they routinely operated above 30,000 feet, our entire defensive strategy collapsed. We lacked time, resources, and technology to develop effective countermeasures. B-29 pilot Colonel Robert Robbins describes the psychological advantage of altitude sanctuary. Knowing enemy fighters couldn't reach us changed everything. We flew straight and level to targets. No evasive maneuvering needed. Bombarders had stable platforms for accurate sighting. Crews stayed calm, knowing the main threat came from mechanical problems, not enemy action. The confidence boost was enormous. We owned the sky above 30,000 feet, and everyone knew it. Kai, 44. Veteran Captain Yoshiro Aoki recalls watching B-29 contrails beyond reach. Each mission brought the same humiliation. We'd climb until our engines failed, achieve maybe one-third the altitude needed, then watch silver contrails drawing lines across our sky. Traditional warrior spirit meant nothing against aluminum and engineering. We were samurai with swords trying to reach the moon. The psychological impact destroyed morale more than combat losses ever could. General Henry Arnold evaluates B-29 program success, despite enormous development costs exceeding the Manhattan Project. The strategic bombing campaign validated every dollar invested in advanced technology. The altitude sanctuary enabled precision attacks and atomic weapon delivery without prohibitive losses. We proved that technological superiority could determine victory without massive ground invasions. The investment in pressurization, supercharging, and defensive systems paid dividends that shaped military aviation for decades. Japanese aircraft designer Tio Doi analyzes Ki-61 limitations against B-29 operations. Our fighter was optimized for combat between 15,000 and 25,000 feet, where most aerial combat occurred. We never anticipated bombers operating routinely above 30,000 feet. Modifying existing designs proved impossible. The engine, airframe, and systems were fundamentally inadequate for extreme altitude. Starting fresh would require years we didn't have, and resources that no longer existed. Squadron leader Major Teruhiko Kobayashi's 244th Senti achieved over 100 victories against American aircraft, but minimal success against B-29s. My pilots included multiple aces with years of experience against fighters and medium bombers. We remained competitive, but B-29s at altitude might as well have been on another planet. Skill became irrelevant when your aircraft cannot physically reach the enemy. We watched our homeland burn while possessing the will, but not the means to defend it. Lieutenant Thomas Cartwright, a navigator aboard a high-altitude aircraft, described the remarkable advantages of operating within a fully pressurized environment. Working at extreme heights without oxygen masks or thick gloves allowed precise chart work, stable instrument readings, and clear communication among crew members. Crews operating without such systems often faced fogged instruments, low temperatures, and reduced concentration, making accurate navigation nearly impossible. The introduction of pressurized cabins represented a breakthrough that multiplied operational effectiveness far beyond what altitude alone could achieve. Ground-based defense units during this period documented the limitations of conventional anti-aircraft systems against aircraft operating at unprecedented altitudes. Theoretical range alone proved meaningless when accuracy fell sharply at those heights. Ammunition was expended in vast quantities with negligible success, as altitude acted as a natural protective barrier for the new generation of aircraft. Maintenance challenges also became a defining factor of the air campaign. Engines required frequent overhauls after only a few high-altitude missions due to extreme mechanical stress. Supercharger failures were common, and oxygen systems demanded constant servicing, with replacement components increasingly scarce. This mechanical attrition gradually reduced the number of operational aircraft, regardless of direct combat outcomes. From observation stations aboard long-range bombers, aircrew reported seeing opposing interceptors struggling to reach their height. Many aircraft appeared to hang motionless near the edge of their climb before stalling and descending. The disparity in performance highlighted how crucial engineering and production capacity had become in modern warfare. Advanced navigation systems, radar equipment, and reliable communication networks enabled coordinated operations across vast distances. Even small details such as heated flight suits, precision gun sights, and durable construction materials reflected the difference in industrial and technological infrastructure among the combatants. The large-scale production of advanced bombers represented a triumph of industrial organization. Precision assembly lines, strict quality control, and advanced material science allowed mass production on an unprecedented scale. In contrast, nations relying on smaller workshops and limited access to high-grade materials struggled to maintain equivalent output. Air forces that attempted to counter high-altitude bombers experimented with numerous interception methods, from night operations to coordinated multidirectional attacks. Yet continual adaptation by the bombers altering routes, altitudes, and timing kept them one step ahead. The experience revealed that adaptability and rapid innovation could outweigh traditional tactical approaches. The aircraft in question was designed with a philosophy centered on technological dominance. Every system from pressurization to remote-controlled defensive turrets was created to overcome environmental and operational challenges of long-range, high-altitude missions. Rather than being merely a bomber, it functioned as an integrated weapon system, shaped by engineering precision. After the conflict, many of the innovations first developed for these aircraft transformed civil and commercial aviation. Pressurization became a universal standard, allowing passenger flights at high altitudes with comfort and safety. Turbo-supercharged engines paved the way for more efficient jet propulsion systems. The lessons learned from this era laid the foundation for post-war aviation and the future of aerospace design. Remote control systems evolve into modern fly-by-wire technology. The technological innovations transform aviation beyond military applications, establishing foundations for modern aerospace industry. Captain Kazuo Noda commands Key 84 Squadron during final homeland defense operations. Japan's most advanced fighter meant nothing against B-29s at altitude. Below 25,000 feet, we could fight effectively. Above that, we were helpless. Pilots would return from missions demoralized, having never fired a shot. The psychological damage exceeded our aircraft losses. We knew we were beaten technologically, which meant we were beaten completely. The B-29 operations vindicate American strategic bombing doctrine through technological superiority demonstration. Altitude sanctuary enables systematic destruction of Japanese military-industrial capacity without prohibitive losses. Strategic effects achieve decision without invasion, validating air power theories. Atomic weapon delivery succeeds due to immunity from interception at operational altitude. The campaign proves decisive air power application through technological advantage rather than mass, establishing precedents for Cold War deterrence strategy. Military leadership gradually recognized that continuing the conflict was unsustainable due to overwhelming technological disparities. The inability to defend against high-altitude operations reflected a broader gap in scientific and industrial capability. Manufacturing infrastructure could not keep pace with the opposing side's production scale while suffering continuous strategic damage. This collective realization influenced the decision to seek an end to hostilities once the means of defense had been exhausted. Veteran flight engineer Chief Master Sergeant Frank Morrison later recalled maintaining the pressurization and propulsion systems that defined high-altitude operations. The equipment was complicated, but dependable when serviced correctly. Turbo systems demanded constant attention, but they gave us power where other engines struggled. Every mechanism represented years of engineering development that many nations simply didn't have. In the end, victory came from technology and production strength as much as from bravery. A surviving interceptor pilot described the extreme physical strain of operating at such heights. Breathing was difficult even with supplemental oxygen, and freezing temperatures made it nearly impossible to control instruments. Watching formation aircraft continue unopposed despite every effort created psychological pressure far beyond normal combat fatigue. The pilot reflected that failure came not from lack of courage, but from the limits of available technology. The contrast in industrial organization was decisive. The advanced bomber program alone consumed more resources than entire air forces elsewhere. Precision engineering, quality control, and large-scale automated production created consistent performance advantages, impossible to replicate under limited wartime conditions. Commanders on both sides recognized that tactical innovation could not offset industrial and technological asymmetry. Strategic air operations during this period demonstrated how science, production, and engineering had become central to modern warfare. The ability to adapt tactics, whether through altitude changes, radar-guided navigation, or coordinated formations, proved more important than traditional measures of battlefield strength. This campaign fundamentally reshaped global understanding of air power. Technology made it possible to achieve strategic effects that once required massive ground operations. Industrial capacity became inseparable from national defense capability. The lessons learned influenced aviation design, strategy, and defense planning well into the post-war era. Historians now view this period as a turning point, when advanced engineering, automation, and industrial efficiency determined outcomes as much as tactics or bravery. The success of long-range, high-altitude operations validated investment in research, manufacturing, and logistics, setting the foundation for modern aerospace development.